Hello everyone, welcome to the lecture number 23 of this NPTEL lecture series on charging infrastructure, and in today's lecture we will see 3-phase AC to DC converter for high power chargers. So generally as of now we have studied the single phase AC DC converters which act as a AC DC conversion stage for the EV charging system. If you recall our EV charging system, if we talk about the power conversion unit of a EV charger, then what we have is our grid, then we have a AC to DC converter, then followed by isolated DC to DC converter. And when we talk about low power applications or low power chargers, that means the chargers going up to 7 kilowatt require, generally those things will be done using onboard chargers, or sometimes even if it is offboard also the power is less, up to 7 kilowatt. So this can be done using single phase grid, that means you require single phase AC to DC power converter at the first stage and then followed by isolated DC to DC converter. However, when we talk about high power chargers going up to 30 kilowatt, or let us say in case of DC chargers where our power levels will be starting from 15 kilowatt greater than 30 kilowatt, there we require 3-phase input, and since we require 3-phase input we require 3-phase AC to DC power converter, and there we cannot use the single phase AC. One possibility is one can use 3 single phase AC to DC power converters, and another possibility is one can use just one converter which can directly convert the 3-phase AC into a DC. We will see that what is a commonly used 3-phase AC to DC power converter in this lecture. And before understanding the 3-phase AC to DC converter, we have seen the concept of PWM, where we know that we can, by varying the turn on time of S1 and S2 switch in the half bridges, we could able to obtain the different values of average pole voltage variation over a carrier cycle. So there we have seen that the average pole voltage variation over the carrier cycle is directly proportional to the amplitude of your modulating signal. So we have derived that equation VAO average over the carrier cycle, or you can say over the switching cycle, is nothing but m VDC by 2 sin omega t, where VDC is the DC link and m is the nothing but ratio of Vm by peak of the modulating wave divided by maximum value your carrier wave can go. So the average variation is dependent upon this, is directly proportional to this m, provided this m is, or the Vm is smaller than, we can say that Vm value is smaller than Vc. That means at every carrier cycle there is a valid comparison and you are changing the switching state in every in each cycle. In each carrier cycle there are changes, the switches will be switching between on to off and off to on. So this is what we have studied. Now let us try to see how we can use this concept of the PWM, or pulse width modulation, and apply it in 3-phase AC to DC converter. Now before that, let us see what is the commonly used, or which is the most commonly used 3-phase AC to DC converter. It is sometimes also called as the front end AC to DC converter, or you can say front end converter, abbreviated FEC. It is a kind of, you can say that, active rectifier. So actively you can apply voltage at the output of the bridge. Now if you look very carefully, the circuit for this particular converter will look like this. You have 3 half bridges, identical half bridges, and having a DC capacitor, and which is supplying to load RL plus V0 output voltage we are getting, and this and in this half bridge, if I draw it more, and in this half bridge what we have is, we have 3 phase input signal coming in, and then we have one inductor, second phase, and then the third phase. And let us define this as A, B, C, and we'll define all the 3 phases has same value of inductances, and this one is then the other side of the phases are connected in a star fashion. Let us define this as small n, and this we can say this particular thing is nothing but VAN of t is nothing but again Vs peak sin omega t. Here we have VBN of t, and here we have VCN of t, and we can write down VAN of t nothing but Vs peak sin omega t, VBN of t Vs peak sin omega t minus 120, and Vcn of t is nothing but Vs peak sin omega t minus 240, phase input. And then we have 3 our inductor, and we have current ISA, ISB, ISC, 3 currents, and here we have capacitance C at the output, and again the same thing which we have done previously. Here we have I converter coming out, here we have IC, and here the average value is coming out, which is IL. Now if you look very carefully in this particular circuit, this is also called as a front end because power can flow from this side to this side, or from by the operation of this we can ensure by using the same converter we can ensure the power can also go from the DC side to the AC side, and if we operate in certain manner the power can flow from AC side to DC side. So this way also power can go, and the other way around also the power can go. And here we have 6 set of switches, let us say S1, S2, S3, S4, S5, S6, and these are all active switches, mostly the same switches which we use in our half bridges. That means it has to block the voltage of V0, however allow current in either direction to flow depending upon if we require the non-unity power factor current drawn from the source, or if we want to pump the power backwards into the source. So now if you look this particular converter, it has a very symmetrical structure, 3 same kind of inductor it requires, 6 set of identical switches it requires, and that is why this converter is very commonly used in case of 3 phase AC to DC converter. Now let us understand the operation of this 3 phase AC to DC converter. Now if we look very carefully at the output, if we have let us say fictitious O point at the output, let us say the output V0 is divided into V0 by 2 and V0 by 2, and it has a fictitious, assume it has a point like here we have fictitious point, one C is there, another C is there, and this kind of thing is there. Here let us divide this as V0 and this is V0 by 2, this is minus V0 by 2, and now if you look is the same thing. If we see the voltage across VAO, then what we will see is that we have by changing the duty ratio of this S1 and S2 switch, or the turn on time of S1 and S2 switch, we can on an carrier cycle period or on a switching cycle period the average value we can vary across this VAO. So we can have the average pole voltage over the carrier cycle, which can be vary depending upon the modulating signal. So if we take the three modulating signal which are varying sinusoidally and have 120-degree phase difference between each other, then we can ensure that we are applying the sinusoidal 120-degree phase difference pole voltage variation at the output. And that's when we can see that from A, B, C point the voltage we can apply between A to 0, and then you can say between A to N the same. I mean this the DC can be dropped across that N to O, this point between this neutral point and the O point, fictitious O point, we will have the constant potential, and thus we can say that we can have the average pole voltage variation which is also varying in a, I mean same as that of the modulating signal, and if that modulating signal is varying with the same frequency as that of the line frequency, then we can ensure that we are also having one more AC source at point A. So we are applying at the output of the half bridge, or you can say at the pole of the half bridge, we can apply the voltage proportional to that of the amplitude of the modulating wave, and thus we can ensure that the average pole voltage variation at the pole of the half bridge here, we can have that average pole voltage variation having the same fundamental frequency 50 Hz as that of the line frequency. And if we can ensure that from the pole A, from the pole point B, and from the pole point C, the average pole voltage variation is having the sinusoidal variation with frequency same as that of the line frequency, and the three pole voltage variations are 120-degree apart, then we can say that there are two AC voltage sources separated by the inductance L. So thus we can draw this single phase equivalent circuit for the, let us say for the fundamental frequency. Let us understand for the fundamental frequency how the single phase equivalent circuit, how it looks like. So fundamental frequency, fundamental frequency means my FM is nothing but equal to Fs, which is nothing but equal to 50 Hz, or the line frequency 50 Hz or 60 Hz, whatever you wanted to take. Let us take 50 Hz. So that is the line frequency. Now the single phase equivalent will be, we have the AC source, and let us define that as Vs of t, that is the supply voltage we are applying, and this is the VAN, VBN, VCN, and we have the inductor L. So for the fundamental frequency, our impedance of that inductor will be j omega L, where omega is nothing but 2 pi Fs. And then we have another voltage source which is nothing but V converter, or we have, I mean the pole voltage of the half bridge, let us define that as a V converter. And if we see very carefully, depending upon the voltage difference between this point and this point, because we have the two voltages so separated by impedance, there will be current which is being drawn from one side to another side, or from the V converter side to Vs side, or from Vs side to the V converter side, between the two AC source, depending upon the instantaneous value of voltages applied, or you can say depending upon the voltage differences. Then let us try to draw in this AC circuit, let us try to draw the phasor diagram. So let us try to draw the phasor diagram for this converter. Phasor diagram. To draw the phasor diagram, what we have is, we know that our Vs of t, if let us say if we are having the current in this direction, so we can write using the KVL, Vs of t is nothing but V converter of t plus j omega L Is. We can write, so we can easily write Vs of t equal to this thing using KVL. So that we can write down V converter of t is nothing but Vs of t minus j omega L Is, And this, if we try to write in phasor form, from this if we can derive that phasor form, we can write V converter phasor is nothing but Vs phasor minus j omega L Is phasor. That means if we assume our phasor diagram to be, our phasor of Vs to be like this is Vs phasor, and its amplitude is nothing but, we can write here the amplitude of Vs phasor is nothing but peak value of the supply voltage, which is nothing but Vs peak. Why I have written this Vs of t just like that, because Vs of t will be the Vs peak sin omega t, or Vs peak sin omega t minus 120, Vs peak minus sin omega t minus 240. Similarly, we can also write our Is of t, since we are assuming that it is a having the unity power factor current drawn, because we want in the 3-phase system to have the unity power factor current drawn. So, we can say Is peak sin omega t, that will be our this thing. So, we can say modulus of Is phasor is nothing but Is peak, maximum value of or the amplitude of the current, this one. Similarly, if we recall our V converter of t is nothing but m VDC by, or here in our case it is m V naught by 2 sin omega t, where m is nothing but Vm by Vc, where the ratio of the amplitude of the modulating signal and the maximum value of the carrier signal. So, we can write then modulus of V converter phasor is nothing but, or you can say the magnitude of V converter vector is nothing but m V naught by 2. So, this is these are the things we obtain. Now, let us try to draw the phasor diagram. So, what we have, let us say this one is a phasor, which is, let us define this phasor as Vs phasor. Now, this Vs phasor, now our requirement is we want our current to be having the unity power factor. That means, whatever the phase angle between the current drawn from the source and the source should be 0. That means, if in case of A phase, current should be Is peak sin omega t, and if the B phase is Vs peak sin omega t minus 120, then current of the B phase should be Is peak sin omega t minus 120, and if the C phase, it is Vs peak sin omega t minus 120. So, current should also be Is peak sin omega t minus 240, and here since we are considering the balanced 3-phase system, all the 3-phase currents are having the same magnitudes. So, we can say that we have the unity power factor current drawn from the source. So, in all the phases one must have the unity power factor current. That means, the phase angle between the voltage source and the current source in each phase should be having 0 degree. So, our Vs phasor is shown over here. Now, let us try to draw the current phasor. Since there is no phase angle between the Vs phasor and Is phasor, so our Is vector will also be in this direction, same 0 phase angle, because to have the unity power factor operation. So, we can write to have the unity power factor operation. Now we have another term which is j omega L Is phasor. So, now the Is phasor is in this direction. So, if my Is phasor is in this direction, so what will be my the phasor, which is omega L Is, and since if you see it is j, that means it is 90 degree shifted, and since it is 90 degree phase shifted and having the minus sign, so what we will get is, we will get a phasor which is nothing but j omega L Is phasor. This corresponds to j omega L Is vector. and the summation of these two is nothing but our V converter phasor. It is V converter. Let's set the angle between them, let's say some delta angle what we have. Now if you look very carefully at any given instance of time, if I can ensure that my Vs or the phasor corresponding to the supply voltage is leading the phasor corresponding to the V converter, then I can ensure that there is a current drawn from the Vs of t, or you can say from the source to the V converter, and that current is having the unity power factor. Similarly, let us take, if you consider the current direction to be in this direction, that means going from the V converter side to the grid side. So, for reverse power flow, means from DC to AC, that means from converter to source. For to have that, the we can write in phasor form V converter phasor to be nothing but Vs phasor minus of minus Is phasor, which is nothing but plus j omega L Is phasor. Because if we assume the current direction to be in this way, in this direction, then our V converter, if we do the KVL, this is for DC to AC power flow. So we can write this using the KVL, and in the phasor form we can write in that way, and that will correspond to, if this is minus j omega L, we can say this is j omega L Is phasor, and that we will have the phasor nothing but slightly adjust the size of these things so that we can fit in this phasor, and then this is nothing but your V converter phasor. So we can say that this particular part says the backward power flow, that means going from DC to AC, and this, and when we are operating the system in this side, we can ensure the forward power flow, that means power going from AC to DC side, and thus just by changing the phase angle between the V converter vector and Vs vector, we can ensure the power flows from either from AC to DC or DC to AC. So with this we can obtain the bidirectional power flow, and that is why the power can flow from the front to the end or end to the front. That is why it is called as a front end converter. Because the power flow can be made, bidirectional. So here we can see that by just changing the phase angle in the positive direction or negative direction, we can allow the power to flow from either direction. Also by changing the magnitude of this phase angle, by changing the magnitude of this delta, we can actually change the size of the phasor, which corresponds to the voltage drop across the inductor. Because inductor we cannot change, omega we cannot change because our AC supply voltage is constant, but one thing we can change is the value of this delta. If we can ensure, if we can somehow make sure our delta is smaller, if we make this kind of arrangement, then the current phasor corresponds to this one will be smaller as compared to here, and this way we can also control the magnitude of current which is flowing from the source to the converter or from the converter to the source. So by changing the sign of, so we can say that by changing the sign of delta, we can change the direction of power flow, and we can say that by changing the value of phase angle delta, we can change the amplitude of phasor corresponds to phasor this drop across inductor. That means we can say the magnitude of current, and since our voltages are constant, we can actually control the amount of power flow from AC to DC or DC to AC. Thus, it is important to ensure the operation of this V converter, or the value of voltage which will be appearing at the output of the half bridge, or you can say the pole of the half bridge. It is very important to ensure that average pole voltage variation should be such that we can able to ensure right amount of power as well as the direction of power is obtained. So, we must ensure that the V converter of T, which is the output of the half bridge, should be generated in a appropriate manner. Now, if you look very carefully, this size of this inductor is one of the critical thing, because this inductor size is responsible for the amount of power flow, and also it is like we are controlling the current through the inductor by applying the voltages across it. One side voltage is constant by the, which is defined by the grid. On the other side, we have this flexibility to apply the variable voltage on this side, obviously over the carrier cycle to have on this side, and in this way we can ensure that IS is controlled. Now, let us try to find out how we can calculate the value of inductor. So, relation of inductor L. Now, what we can do is, if we just try to find the phasor, we know this phasor is Vs phasor, this is minus j omega L Is phasor. Assume the power is going from AC to DC, and we have V converter phasor. Now, we can write that modulus of V converter is nothing but equal to, if we do apply the Pythagoras principle, it is nothing but minus j omega L Is square plus Vs phasor, magnitude of Vs phasor square. And this we can write down that omega square L square is nothing but modulus of Is phasor square plus modulus of Vs square. Now, this is nothing but equal to omega square L square Is peak square plus Vs peak square, and we know that modulus of V converter is nothing but m V naught by 2, and this is, this we can actually take the square both side, and finally when we rearrange, what we will get is L square is nothing but m V naught square minus Vs peak square divided by omega square Is peak square. Now, this, when we will write down, this is L is nothing but m V naught by 2 square minus Vs peak square divided by, we can write 2 pi Fs into Is peak square. Here our m is modulation index, which is in our control, and we can vary this modulation index from, generally it is been kept between 0.8 to 0.9 generally in normal operation. And we know our Fs is nothing but equal to Fm is nothing but equal to 50 hertz, and our Is peak is nothing but peak of the phase current. V naught is the DC link voltage, which is again given specification. This we can obtain it from specification by doing the power balance and knowing the power level of the load. V naught is a DC link, Vs peak is the peak of the phase voltage, and accordingly we can calculate our inductance value. And finally, once we calculate the inductor value, we must ensure that the voltage drop across inductor must be within 10% of the supply voltage. Again, this voltage drop is in terms of a fundamental component, so this has to be ensured. This has to be ensured. So what we do is we can define these values and then calculate the L, and then one can cross verify with the whether this voltage drop across inductor in the, obviously in the fundamental frequency sense, in the fundamental frequency, for the fundamental frequency must be within 10% of the supply voltage. This has to be ensured at last. So one can define this term, because this is again the design freedom which designer has. This is input, this is the things which you obtain from the specification, these all things from specification you will obtain. So we can calculate the inductance value L, but then finally at last we must ensure that this L, the voltage drop across L, should be within 10% of the supply voltage, otherwise most of the voltage will drop across inductor, and you can say that DC bus utilization will be lesser. So we must ensure that the inductor voltage must be within 10% of the supply voltage. And if you look very carefully, this inductor will always be in conduction throughout the line cycle, because it is at the front side. So if you see the RMS current, if we see the RMS current of inductor, RMS current of this inductor is nothing but equal to Is peak by root 2, simply because we can, we can write this one root mean square. So root of mean 1 by t going from 0 to t, you can say Is peak sin omega t, obviously square dt. If we do that, we will finally get Is peak by root 2, and thus we can easily able to, we can size our inductor accordingly. Now comes our, if we look very carefully in this converter, we have our capacitor also. So we will do the design of this capacitor in the next lecture. So in this lecture we have seen the operation of front end 3-phase AC DC converter, and we have seen how we can allow the power to flow in the either direction by just changing the sign of the phase angle between the V converter phasor and the Vs phasor, and we have also seen how we can size the inductor in this particular converter. And we will, in the next class we will see how we can size this capacitance value, and then we will further improvise our understanding about the operation, and then try to find how we can define the closed loop control of this particular converter. So thank you very much for attending this lecture. We will meet in the next lecture.